Okay, let's take a look at r squared as I got screwed up in class. So let's look at it afresh here. So again, the idea is that we have some points here. We're going to maybe fit a line to them. And this is y0, y1, y2, y3 here for heights. And then on the graph itself of the line, that would be y0 hat, y1 hat, y2 hat, y3 hat. So those are the predicted values. And if we look at the variation times n, what that is it's just the sum over all the i's of each yi minus the average of the y's squared. Okay, so it's just a particular statistical tool, and see what we're doing is we are thinking of the y's just as their values. So let me y1 was about there and y0 was about there. So here's y3, y2, y1, y0. Those are the heights, and so we just are asking, y bar is probably somewhere in here, and so again, y bar might be somewhere right around here, and we're just taking that distance, the actual value there from each of those, taking that distance here and squaring it and adding those all up. So we can also call this the sum of squares total, or maybe TO, just to make sure we've got total, because there's also something called sum of squares treatment. Okay, so we've got that. Now I can do some little bit of fun algebra here with adding and subtracting, or actually subtracting and then adding the same thing. So suppose I take those predicted values and subtract and add them, and do that. Okay, well that's still my sum of squares total. Okay, but now I can multiply that out, and so we'll have the sum over the i's. We'll have the yi minus yi bar squared term. Then we'll have this mixed term, yi minus yi hat times yi hat minus y bar, and then plus yi hat minus y bar squared. Okay, so we get that. Now, here is our predicted value, our f of x, I. And so what we have here is we have the sum over I of the yi minus yi hat. And this we call our sum of squares residual. Then I've got this middle term here. Okay, so yi hat. And then the final term. Okay, that's over i's, yi hat minus y bar squared. And so I'm just going to call this a mixed term. And this term, we're looking at yi hat minus y bar. So as we come back here, well, let's redraw it again. So, okay, so here's y bar somewhere in the middle of all those y's. And here are our yi hats. So, you know, here's y0 hat, y1 hat, y2 hat, y3 hat. And so we're just looking at these distances squared. And so the question becomes, and here we're going to call this, I'm going to call it sum of squares model. So I guess I'll put it up here, sum of squares model. Now, so what we have at this point is sum of squares residual, plus I'm going to write sum of squares model, plus that mixed term is equal to the sum of squares total. Now the sum of squares model could also be called sum of squares treatments in the right situation. Okay, so now let's look at this mixed term. Well, what I'm going to say is I'm just going to claim it 0 and then show with an example here, right here, that at least in this example it's 0. So here's some data. Oh, that's kind of funny. Let's switch to the non-projection mode, sort of all by its lonesome. So let me turn those off for a minute. So there are my data. Then I added this least squares line, and just to show the predicted values, I took the b times the x1 plus a and plotted those points, and you see they're right along that line. And then what I did, oops, not there, I want it here. There we go. I took y2 and defined it as b times x1 plus a. So in other words, I just made these y values again up here in the b x1 plus a section. So I just made them again, but as a list, and then I summed up the list, and I took the y, in this case n instead of I. Quit that. I don't want that there. Put that down. Okay. So I took the y1i minus the y2. y2 is the predicted value. So I did that. Now let's see. Can I? Well, I don't know if I can. Yeah. Okay. Whoops. There we go. There's all of it. So I took that formula we had. I took the y1 minus the y1 hat. That's my y2 up there. Y1 hat. And then times, so this is just the mixed term without the 2 in front. And I took my y1 hat, n in this case, minus the mean of the i's. And notice that I got something times 10 to the negative 15th. So up to round off error, I got 0. Okay, so here's an example showing that that mixed term is indeed 0. So let's come back to that. So that mixed term is 0. So what that says is that my sum of squares total is just made up of the sum of squares residuals, the errors, between real data and predicted. And then plus the sum of squares mean. Okay. And so then the r squared, if I divide everything by sum of squares total, you see you get sum of squares residual. So this is again the error between the real and predicted values. And then this over here, the SS model, again, it's just a portion. It's just saying it's a portion of the sum of squares total, but it's the variation accounted for by the model. And then the error is the rest of the variation. And so if we take sum of squares residual divided by sum of squares total plus sum of squares model over sum of squares total, we get 1. And then so the r squared is defined by, or can be defined by, 1 minus the sum of squares residual over the sum of squares total, which is then the sum of squares model over the sum of squares total. And so this is the proportion, you see. So r squared then is the proportion of the variation in y explained by the model. So to show a little more, to kind of compare a couple things. So you see, you could have, I'm going to just put 4 y values in here. So there are my 4 y values. Well, if they happen to go with x values such that there's the 1 y value, there's the other second y value, there's the third y value, there's the fourth y value, you see the model explains the variation, because the y values with their given x values land right on that model. On the other hand, I could have those same y values and in this case it could be that that one goes with the first x value, this one, well, we'll go with this one goes with the second x value, this one goes with the third x value, and this one goes with the fourth x value. And so the model might look, you know, something like this. And in this case, you see the model explains very little of the variation. Okay, because, you know, I see this variation in the y's here, but the model doesn't really predict where that variation is going to be, right? You know, the model says, oh, the y is going to be here, but wow, it's way up there, and you know, here it says it's going to be there, and it's not that far up. So the model doesn't do a very good job of predicting that variation in the y value. And so this would have, you know, an r squared near 1, and this might have an r squared near 0. Okay, because it's the proportion explained by the model. So there we go. Hopefully that's a little better treatment of r squared than what I did in class.